Let's talk a bit about reliability issues in protection. And I would like to start with just 3 statements on this topic. On one side, we should have in mind, if something goes wrong in protection, it may have severe impact. It can result in blackouts. So you as a protection engineer may become famous because the whole city is dark. It can also result in damage of equipment. It can result in injured people or whatever. That means the technology we are dealing with here is not a gaming thing. It is a thing where we have to pay severe attention that it really works. But we also know we cannot reach 100% reliability. That means whatever we do, there is a certain risk that the system doesn't work as desired. And this risk is accepted in all other areas as well as in protection. But we must do our best to minimize this risk, of course. We must do our best, but we must also have in mind we have economical constraints. We cannot do as much investment as we would like to do to optimize the system. We always have economical constraints. That means the amount of equipment we are allowed to install depends on, and also the manpower we have available depends on the voltage level and also on other quantities. You can imagine if you want to do protection for a simple distribution feeder, this has to be cheaper than the investment to protect a 400 kilovolt transmission line. That means there are also economical constraints. And in this framework, you have to define solutions, and state-of-the-art solutions have been developed in the companies. They are sometimes different in the different companies, also in the different countries. That means different ways of doing things are established, but they also all have these considerations in the background. So that is one introductional remark. Now I would look a little bit into some theoretical considerations. You often hear about things like mean time between failures, mean time to repair, outage rates, and so on. What is that in this context? Often we assume a simple 2-stage model to describe an electronic component. That means you say you have an electronic device, it's either in operation or it has a failure. And you can draw a diagram like this. That means the device is in operation, after some time it fails, then it's repaired or replaced, then it's in operation again, and it fails. Of course, these time slots for the operational time should be a bit longer than indicated here in this diagram. But that type of model is often used to describe stochastic outages. And that is the important thing with that. These definitions which are used to describe the behavior and to describe the reliability of an electronic device, they are designed for stochastic outages of devices. We sometimes mention, for instance, the outage frequency. That means how many outages do you have per year, or does a component in an average have per year or per 100 years. That is so the outage frequency. Imagine, for instance, if you have an outage frequency of 1 outage per 100 years, that would mean if we have 100 devices in operation, 1 is expected to fail within 1 year. But you must have in mind it's only an average figure. It can also be 2 or it can be 0. The outage can be tomorrow or it can be at the end of the year. So these outage frequency are stochastic quantities. They are the more precise, the bigger the quantity of devices you have. Outage frequencies of industrial electronic equipment are typically in the range of 0.1%. That means you have typically an outage every 1,000 years. Or you can say if you have 1,000 relays in operation or 1,000 devices in operation, you can expect one stochastic outage. The next quantity, which is also often mentioned, is the so-called MTBF. That is called mean time between failures. That is just the average time if a device is in operation. How long will it take as an average until it fails again? And that should be a thing which is pretty long. You can calculate that. There are defined methods to calculate that. I personally think that these calculations are not really relevant for our field of application, for our protection field. I will explain the reason later, but that term is sometimes used. Another thing is the mean time to repair. How long does it take to repair or to replace a device? And then you have the so-called availability. That is a figure which is typically something like 99.9%. That is the percentage of the time where the device is in operation. So these quantities are defined for simple electronic devices which can either be in operation or defective. But reality in protection is a bit more complex. One thing is the question, what is a failure? If a relay just fails, the good thing with digital relays is if they fail, they will alarm. That means the control center knows there is something wrong in the relay, protection doesn't work, you can or you have to take the line out of operation, you replace it and it goes. The problem is if the relay is dead, it has a failure, you don't realize it because, for instance, the wiring is broken to the circuit breaker. You may have a missing trip. That means you have a short circuit, the relay does not trip because of a failure. That type of failure is called missing trip, but we have another type of failure, and that is called unwanted trip. Theoretically, it's possible that a protection relay gives a trip command, although there is no fault on a trip. That means we can fail in two different directions, missing trip or unwanted trip. Both are things we don't like. So that means already that this simple two-stage diagram in operation and failure is a simplification which doesn't really fit to protection. And there is another thing which has to be taken into account. This diagram and also these quantities refer to stochastic failures. If I remember the type of failures I had to deal with during my active time, the majority were not the results of stochastic failures. The majority were results of design problems or setting problems. And that are not stochastic things. For instance, if you have a protection concept where somebody did a wrong design because a signal was misinterpreted, or we even have a software bug in the protection relay, it's not a stochastic thing. It's always there and it shows up in a dedicated situation. Or if you have a setting problem, this problem is always there, but it becomes only visible if you have a fault at a location where this setting problem results in wrong reaction. And this has to be taken into account. Before we look into that a little bit deeper, I just want to introduce two terms in this context, unwanted trip and missing trip, that are two terms which are often used in protection, that are the terms dependability or security. Dependability addresses, can we depend on the relay that it will trip if there is a fault in the zone? That means the dependability addresses the risk of a missing trip. On the other hand, the security addresses the risk of an unwanted operation. That means if we want to increase the security of a protection scheme, we want to reduce the risk of an unwanted trip on a fault outside the protected zone. And these two issues have to be balanced. If we, for instance, increase the dependability, we may decrease the security. That means we must make up our mind what is the proper balance for that. So that were some theoretical considerations. And now the question is, what can we as protection engineers do to improve the reliability with a limited budget? Think of, we always have these economical constraints, and it's important if we say we want to improve something, where to do the investment. You can, for instance, compare that with your house. You want to make your house burglar proof. And then there are people who invest a lot of money into the front door, make a very safe front doors that no burglar is able to come in. But he doesn't look at the back door he has in the house. And then he comes in through the back door. It's very easy to come in. And in this simple example, you see it was a wrong investment to invest all the money into the front door. You should have taken half of the money and invested into the back door. And we have a little bit a similar situation in protection. We have to look, where do problems come from and where should we do something to improve the situation. And there we have to look at these three classes of problems: stochastic failures, design problems, and setting problems. What can we do to reduce the rate of stochastic failures? We need higher reliability of devices. That is a thing of a manufacturer. And we invested really a lot of brain to design the devices in a way that the outage rate is pretty low. You know, our technology doesn't accept fans. That means we have cases which has no ventilation, and electronic components produce a lot of heat. We must get the heat out of the box. And that is a design question. You must think about how to arrange the components inside the box that you don't get hot spots. And especially you don't want hot spots near electrolytic capacitors, because they are pretty much sensitive on that. That means reliability of devices on one hand is first of all a manufacturer issue, but not only, you will see later on. Also the selection of components used to build protection relay is such a thing. And with all the measures, state-of-the-art design, you end up on a certain reliability level. Not at 100%. You will never reach the 100%. Then, and that is now the question of the user of protection relays, we typically have redundancy. That means we must design our protection concept in a way that if one device fails for whatever reason, because the relay is out of order, the circuit breaker doesn't work, the wiring is damaged or whatever, if one relay doesn't work, there must be something else. There must be a backup for that. And that is an important design criteria for the protection concept. You always have to think, if this protection relay fails, who is going to do the job? But there are also some other measures to reduce the failure rate. One thing is better maintenance. Are your substations regularly maintained? But also, what do you do as maintenance? The protection relay itself is basically maintenance free. You may have to look, for instance, at the wiring. Is there anything wrong in the wiring? Is the insulation of the wires okay, or whatever? Another thing is the environmental conditions. Where are the relays installed? And I can tell you, I've seen relays where you couldn't see any colors on the components. So they were installed in a dusty area, or you even may have corrosive gases there. And of course, if you have these conditions, the relay will work, but after some time you will have an increased failure rate. And you have to take that into account, or you have to think about, does it make sense to install the relays in a better place? And the last thing I mentioned here is the question, how long do you keep relays in operation? Do you preventive replacement with a certain concept if the relays reach a certain age, or do you just wait until they fails? Also there, different concepts are in work. All these things refer mainly to stochastic failures. Then we have the design problems, and that is a thing which affects the manufacturers of relays, but also the users. The manufacturers have to look at their development processes, design, also testing. Are the processes okay? Is the experience and skill level okay? Do we have proper test procedures? But that also refers to those people who build the protections or who design the protection schemes and also do the commissioning. Also there you can make faults. And also there, these mistakes which are done, and also there nobody will work without mistakes. Mistakes happen. There the question is, do we have processes to detect mistakes? Do we have sufficient skill level for the people working with that, and so on. And the same refers to setting. Also there we must have a look, is the responsibility clear? I found many cases where we had to analyze protection maloperations, and it was not clear who had the responsibility to calculate the protection settings. To calculate the protection settings, you need certain knowledge about the network. You cannot tell the commissioning guy, yeah, just you know the relay, please do the settings. You need some knowledge about the network, sometimes a bit more, sometimes a bit less, but you need some knowledge about the network, and it must be clear who has the responsibility. And also there, it may be necessary, especially if you have fluctuation of staff in this area, you must think about, could this area be the back door where the problem comes in? No? You invest a lot of money into building redundancy, but on the other hand, the setting calculations are wrong. And another issue is with settings. You calculate the settings today based on the network situation you have today. Then your system may grow or may change, because you have new renewables installed there, the load grows and whatever. And that means after some time, the settings may no longer be valid. You may have to adapt the settings. Also, this procedure must be looked at carefully. So you see, there are different components you have to have a look at if you want to improve the reliability of the system. It is not only the MTBF of the protection relay, and that is the message I want to give with this chapter. and think about this example with front door and back door. I think that's a good equivalent in this case to motivate investment at the right point. So that is the end of the reliability chapter, and after that we will do the part 2 of building a protection scheme.